Thank you. Thank you, everybody. Thank you. Thank you so much, Jennifer, for the introduction, and thank you to the team at Container Solutions who've put all of this together. It's kind of awesome to see so many friendly faces, but also so many new faces. But I haven't spoke to an audience this size for about 4 years, so it's also a little bit nerve-wracking. I'm glad that I'm going first so that I can get off and enjoy a cup of coffee and watch the rest of the day. So, welcome. Good morning to everybody. I hope you're having a fantastic day so far, and I really hope you have a wonderful conference today and tomorrow with us here in London. My name is Jamie Dobson. I am the founder, the chief exec of a company called Container Solutions, and we just help our customers do really cool stuff with the cloud. Today, we're going to be talking about artificial intelligence. Not many people realize this, but the history of computing is really just the history of electricity and the devices we invented to manipulate it. There's a bit of a funny echo, on the sound. Anyway, so many people don't realize that, the history of the computing really is the history of electricity, and a lot of these devices we created were at the time dismissed as impractical. They were solutions without problems. However, with the benefit of hindsight, we could see that these devices went on to change the world, and they changed the way we interact with it. I feel like history is currently repeating itself. Artificial intelligence can write essays, can write poetry, is not bad at writing Terraform scripts, can program in Java, as we're going to see later, can offer advice on cloud-native strategy, can diagnose some forms of cancer better than human physicians, and can predict the 3D structure of proteins based on amino acid sequences. That's a problem we've been trying to solve for 50 years unsuccessfully. So the three things we're going to do today, let's look at history and see what lessons we can take from it that might be applied right now. Secondly, let's talk about us. What might it mean for us as programmers, cloud engineers, or indeed any type of knowledge worker within our community? And finally, it would be naive to think that the changes that are happening right now will not affect society more widely. So what does this mean for humanity? So originally, Alessandro Volta created the battery to win an argument against his friend Galvani. They were arguing about what happens, why does a frog's leg twitch when you touch it with a bit of wire? The battery was a solution without a problem. It found its killer application in the telegraph. So the telegraph is a remarkably simple system. It has a switch, an electrical wire, a bunch of relays to amplify the signal, and then at the other end, the process is reversed and the message is decoded. Now, not far from here in North London, the telegraph was tested on a 13-mile stretch of railway line. So back then, the trains were coordinated with error-prone signals and even more error-prone schedules. As soon as the train broke down, of course, the pre-printed schedules made absolutely no sense. Now, two very hapless bank robbers made their escape on a train where this line had been installed. The joy they had must have been short-lived, because when they got to the next train station, the police were waiting for them. The message over the telegraph wire had arrived quicker than the train had gone. It travelled 300 million miles per hour quicker, actually. And so the battery found its killer app with the telegraph, and the telegraph itself found its killer application coordinating trains, schedules, and their passengers, etc., etc. We jump forward to 1876, 100 years before I was born. Alexander Graham Bell invents the harmonic telegraph. It's a mechanism for sending voice over the telegraph wire. We call this the telephone. I personally love this design. So on the left-hand side, you see a diaphragm, and hung from the diaphragm on a bit of thread is a needle. The sound waves going into it forced the needle to vibrate ever so slightly, which created or altered the resistance in the circuit that it was part of. The resistance then created a unique electrical signal which was analogous to the sound wave that had gone in, and at the other end, the process was reversed, and you could hear the sound coming out. This brings us to the first lesson I wanted to teach today, I wanted to share. Alexander Graham Bell was not a practical person. He wasn't a hands-on inventor. He didn't know what to do with the patent that had been awarded. So he tried to sell it to Western Union, who had made all of their money with the telegraph. Western Union laughed. They said, Why would anybody want a telephone in their houses when you can just walk to the end of the street, send a telegraph and get a response back a few hours later? They seriously said that. And the problem for Western Union, of course, is that they had a legacy technology, they were dedicated to its incremental development, and power struggles within the organisation led to what we can see in hindsight was really quite bonkers decision-making. The question then we should be asking ourselves is, how many companies are passing on AI right now because of their dedication to their legacy technology? And how many companies are still passing on cloud as if that isn't going to be a thing? So these technologies were ridiculed, rejected. They had no real-world applications until, of course, a real-world application presented itself. Jump forward to 1904, and we invent the vacuum tube. So this was a super versatile device. It could pick up weak radio waves and amplify them enough to drive a loudspeaker. This meant they were destined to influence the development of radio, television, and telecommunications. Long-distance phone calls were not possible until we invented the vacuum tube, but it was just a souped-up light bulb. It had a vacuum encased in glass, a filament, and some wires running into and out of it. What that actually meant was when the light bulb was switched off, it could represent the binary number 0, and when it was switched on, it could represent the binary number 1. So as well as being destined to influence telecommunication, vacuum tubes were used in the first electronic computing devices. That work slowed down in the First World War and then picked up speed in the Second World War, where we started to find practical uses for the computer. The problem with these machines, however, is that they were absolutely massive. This is the ENIAC, one of the most advanced computers at the time. It weighed 30 tons, so it was possible for a B-52 bomber to carry it, but it was 170 square meters, which means it would have never fitted in. The other problem, of course, was the vacuum tube itself. Light bulbs get hot, so they melt the machinery which they're part of. They attract moths, which means the operators were always debugging their machines, literally. And like all light bulbs, they eventually pop. So the vacuum tubes in this machine were really the best you could buy at the time. They lasted for 3,000 hours, but it was made of 18,000. So statistically, a light bulb would go every few minutes. This led to the ludicrous situation where soldiers were deployed around the machine with baskets of vacuum tubes ready to quickly replace them while the computer was running. So for those people who work in infrastructure today, if you think your job's difficult, imagine doing that, right? And so the promise of the vacuum tube and the computers really was a promise that remained unfulfilled. We jump forward to 1947 and we invent the transistor. Now, the transistor was absolutely brilliant. They called it the fabulous midget. It did everything a vacuum tube could do. It amplified signals and it could act as a switch. But of course, it was smaller, more resilient, and had much lower power needs. This meant that the radios we used to own. Does anybody have any grandparents who used to have one of them in their house? Yeah, my grandparents had one of these. Sorry, they still got one? You was trained on them. Okay, we have a time traveller in our midst. Okay, so this was a desktop radio. They were massive, and that's because inside it was full of vacuum tubes. The transistor radio was full of transistors, and it could be powered by Alessandro Volta's batteries, and it could therefore fit in your pocket. So the transistor let us miniaturize everything. The race was now on to make genuine electronic computers. 12 years later, 1959, Robert Noyce, Jack Kilby independently invent the integrated circuit, or the microchip. Surprise, surprise, it was completely ridiculed, rejected, and the main complaints were threefold. Number one, the best electronic components at the time were not made from silicon. That's true. Number two, the manufacturing process was completely error-prone. That was also true. And number three, all of the world's circuit designers would be unemployed. These were the three main pieces of resistance. This was a solution without a problem. And the microchip languished for a few years, floating around, not really doing anything. But then history changed and a problem was provided. NASA needed guidance computers for their Apollo moon mission, and the US Department of Defense needed the same thing for the Minutemen ballistic missiles. So the killer app for the microchip was literally a missile that was, at least designed to be sent to kill other people. So they found their killer application, and this, of course, led to the successful use of microchips in the first computers. Does anybody recognise this? I did see my friend Steve Freeman earlier. I reckon he might know what this is. Does anybody recognise that computer? This is the Leo, the Lions Electronic Office. It too was ridiculed and rejected. The British press said, "What are you going to use this brain for? To calculate the number of beans we should put on toast, or to calculate the amount of Swiss roll we'll need during the Easter holidays?" But despite the mockery, Leo could do the work of 300 clerks with annual running costs equivalent of just 50. The problem with Leo and machines like it is that you had to batch up a bunch of punch cards, stick them in a queue, and hand them to a computer operator. You'd get your results back probably in days, and often the results were a core dump because your program had a bug in it, right? The way you fixed a bug was by patching the holes there with a piece of sellotape. That's why we call fixing a running software program patching it. That's why we say we're going to patch this software. Now, things started to change for the better in the 60s. So in 1968, these two kids returned with all of their schoolmates to their school in Seattle, and they found this peculiar machine. It's an AS33 teletype. It wasn't a computer, but it also wasn't just a typewriter either. It was an electronical contraption that linked the world of Alexander Graham Bell to the then emerging digital and information world which was to come next. It was connected to a GE 635 mainframe computer, which wasn't special for any other reason than it had the Dartmouth time-sharing software system built into it. Time-sharing gave users the illusion that they had unfettered access to the machine. Now, the team at Dartford College also invented BASIC, not the world's first, but an early, sensible, high-level programming language. So that meant these students could have what felt like unfettered and personal access to a machine, and they didn't have to program it with punch cards. That was the first titanic force at the time, in the late 60s, early 70s. The second titanic force was the team at Intel. So after Robert Noyce invented the microchip, he founded Intel, and in 1971, they accidentally invented a computer on a chip. Now, what they'd done is figured out that, hey, if we put programs on memory, rather than have all these punch cards, and then we load those programs into this chip, they called it a microprocessor, by the way, then you could do little computational functions. They were primed to smash these two forces together. Intel should have been the company that invented the personal computer, and yet they thought the idea was ridiculous. Exactly like Western Union, they said, why would anybody want a computer in their houses? Right? This is ridiculous. Nobody would ever use them. We don't need that many computers, etc., etc. So even though the team at Intel was young and very creative in 1971, they too had a legacy technology. Memory chips was their main business. They were committed to its incremental improvement, and the power struggles within the org, to us, in hindsight, makes their decision-making look utterly insane. So in the end, the personal computer was invented by a guy called Ed Roberts. He basically stuck input and output devices onto an Intel microprocessor with the key, and there's a key missing ingredient, is once he'd done this, there was no way to interact with that machine. So those two students who had got access in their high school had said to each other, we've got to do a BASIC for the Altair. At this point in the story, they were both studying because the parents wanted them to stop messing around with computer programming and get proper jobs. One of them was studying law, the other one was studying engineering. Those kids had become obsessed with BASIC, and I can relate to that because I was 9 when I first programmed BASIC on a computer, first on a BBC and then on a Commodore 64. And I too became obsessed with programming and what could be done with computers. Those guys were still obsessed. So they wrote the BASIC for the Altair, and the Altair itself was rejected and ridiculed by all of these massive computer companies. Do any of us know what those computer companies were called? No, because they all went bankrupt. The personal computer became the dominant force in computing, and that all started in 1975 with this. The confidence that those two programmers got from that work and the money they earned led to them starting their own company, and it had never been done before, or a company like that was quite unique. And because they created software for microprocessors, they called the company Microsoft. They dropped the hyphen in 1976 to become Microsoft as we know it today. And 50 years later, they're a huge driving force in the advancement and adoption of artificial intelligence. What does all of this teach us, or what should we take away from this? When you're in an epoch-changing moment, you cannot see that you're in it. It's very difficult to see it. Robert Noyce had no idea what to do with the microchip and had even less of an idea what to do with the microprocessor. Western Union, it was the same. The world was changing right in front of them, but they rejected the telephone as something that would never work. The personal computer, equally ridiculed, rejected. Up until maybe the last 6 to 12 months, I don't think anybody was taking artificial intelligence seriously. But I'm certain, in hindsight, we will all see two things. Firstly, that the noughties was an epoch-changing moment because we started to cloudify society. And I think we'll look back at that period like we now look back on 1947 and 1971. I also think, and I think the second epoch-changing moment is happening right now with the arrival of sensible uses for artificial intelligence. I think for the last few years, we couldn't quite work out what to do with it, but we have worked out what to do with it now. What on earth does all of this mean for us? I'm just going to get a time check, Jen. How am I doing on time?
8 minutes.
8 minutes. Okay. Okay. I need to hurry up. What does this mean for us? So my first big project I worked on was over at KLM in the Netherlands, and I was leading a team, and our job was to recreate the functionality of a travel agent online. So for the very first time, you'd be able to search for your flight, pay for it, check in, etc., etc. So me and the team were working together to essentially do to the travel agents what Netflix had done to the video shop and Amazon had done to bookstores. And it took us about 10 or 11 months, and there were 10 or 12 people working on this big Java application. There were probably only a few key algorithms in that whole system. Many of them were developed under my supervision by my teammates who were slightly less experienced than me. But most of the work, it required us to be talented, but most of it was repetitive. We built the software with Ant. Does anybody remember that? Cruise control was our continuous integration server. But we spent a ton of time on test data, mocks, stubs, and lots of glue code that would connect us to these back office systems like Amadeus. So in preparation for this talk, I've been experimenting. I wrote a Java program. I can still do it. Don't say a word, right? I wrote a Java program in about 20 minutes. And what I did is I told ChatGPT the design constraints I was interested in, what I was trying to build, and then I got busy. And I managed to do in 20 minutes what I think would have taken me a few days if I was just working on my own from memory and using Stack Overflow, etc. to guide me. That made me think the system we built for KLM, I reckon 2 of us from the team back then could have built it in maybe, I don't know, 6 or 7 weeks, rather than the months and months and months that it actually took us to build. So Kent Beck wrote about this recently. He said he gets the feeling 90% of his skills are now redundant, and the other 10% have changed in value by a factor of 10, a factor of 100, or maybe even a factor of 1,000. I think it's the same for cloud stuff. Cloud stuff is also a lot of this, YAML, configuration code, etc. So my prediction is, or my advice or my thinking is something along these lines. We need to learn to work with these productivity tools. So when I started my career, there was no such thing as an integrated development environment. So Eclipse and Visual Studio was emerging, there was Turbo Pascal, but these were new tools. A lot of us had to learn how to use these productivity tools, and it gave us, an advantage over other people in the workplace. We need to learn to use these tools, because I think almost certainly they're going to be part of the work that we do moving forward. But there is a question: if these tools genuinely make us 100 times more productive, maybe there's too many engineers in the world right now. Alternatively, maybe the world is about to rapidly cloudify because everything's going to speed up, because there's enough of us with the assistance of AI to get moving really quickly on these things. Now, moving away from computing, I just wanted to show you this. I can't actually see this without my reading glasses. So you can scan this QR code. So I want to thank my colleague Julian for helping me on this. This is a chat bot. Let me see if I can bring that up. I'm going to look at the screen, it's easier. This is a chatbot. So we fed this chatbot all of my notes from the books I've written, from the Confluence pages we've got, etc., and we wanted to know if it could give sensible advice on cloud native transformation. And actually, it does. So here's the question: how do containers, microservices, and platforms like Kubernetes fit into the cloud native ecosystem? It gives you reasonably sensible answers. Now, the way to get to these answers would be threefold, typically. Number one, you've got to buy the book or download it for free from the website, which you can do, but then you've got to read it, and then you've got to use the practices in it for a few years to build up that experience. You could work with a consultant like me, but there is now a third option, which is you can work with a chatbot like this one that understands cloud-native strategy and cloud-native transformation. Now, you've got to take its advice with a pinch of salt. Because it sometimes gets things wrong. It's definitely the machine. It's not what I put into it. It's definitely the machine. So this is interesting. If these tools are making us more productive as programmers, and they're making us more, and they're giving us consultancy advice, what does that mean for us moving forward? So this is what I meant earlier when I said the age of artificial intelligence is already here. So the question remains: what is it that we're going to do about it? Because unless you're close to retirement, I think this is going to be a big part of your working life. And if you think people are not taking this seriously, you're mistaken. A lot of companies out there are currently not hiring because they want to see what they can do with tools like this in terms of productivity. So this is a serious matter. And Pearson, which is an education company, their share price dropped recently because they're worried, or at least the stock market thinks, that artificial intelligence is going to disrupt their business model. This is the scary graph. This is the graph that nobody wants to talk about, or I think most people don't understand. So for as long as capitalism has been rumbling along, we've been innovating. So recessions come, we run out of money, and we have to do more with less. So we innovate, we automate. And in the past, that wasn't really a problem in terms of employment, because what would happen is you'd automate some so-called low-level work. The people who did those jobs, of course, it's extremely traumatic to be made redundant, even more traumatic for your job to just go away because it's now done by a machine, because where will you do your work? But nevertheless, that leads to high-level jobs, more jobs than the original one created. And this is why productivity constantly increases, and along with it, employment constantly increases. But something changed in the noughties. We started an age of jobless recoveries. A jobless recovery is what happens when, number one, there's a recession, number two, we automate and we innovate, but number three, productivity revenue comes back, but the jobs do not. This is why the employment line is plateauing. So we are more productive than we've ever been, and yet employment is exactly the same. This trend is only going to develop further or continue further with the use of artificial intelligence. This is a report from McKinsey, but there's loads of reports out there, and they all say more or less the same thing. Between 300 and 800 million people on this planet will be affected in the next 7 years because of artificial intelligence. Up to 375 million of them will need to switch occupational categories. That's a posh way of saying they'll have to get a different job. They'll have to retrain and do something else. If this is the next 7 years, what do we think is going to happen in the subsequent 7 years? Don't forget the story of 1971, when Intel in only a decade went from a basic microchip to a computer on a chip. Moore's law isn't a sort of, to Intel at least, Moore's law was a prophecy that was theirs to fulfill. It's a relentless power or a relentless force in technology. It was true then and it's true now. These technologies will develop exponentially. Artificial intelligences already train other artificial intelligences. So if we think 375 million people are going to be disrupted or dislodged from their jobs in the next 7 years, what on earth do we think is going to happen in the subsequent 7 years and the 7 years after that? Eric Brynjolfsson, one of my favourite writers on this matter, he makes this very clear. There is no concrete economic law that says innovation will lead to more jobs. That's been a heuristic for the last 100, 150 years, but that no longer holds. So we will move to a point where there are more, there are less and less jobs for all of us to do. And typically, we always thought automation was about robotics, factories, agriculture, all the heavy lifting that nobody wants to do anyway. But all of a sudden, there's this huge category of jobs, computer programming, strategic advice, apparently, I'm out of a job, computer programming, cloud engineering, etc., that is susceptible to automation. And AI is really like a teenager. It's quick, we're amazed by some of the things it comes up with, but it makes howling errors. It's within those errors that we get to use our experience to guide it and train it. But if AI is a teenager now, what's it going to be in 5 or 10 years? It's going to be an adult. And all pupils eventually overtake their masters. This, I am absolutely certain, is in the post for us as an industry, and it's in the post for us as a society. Should we be worried? Well, I think ambivalence is more normal. We should be worried. We should, because this is going to have a huge impact on the world that we live in. Exactly the same way that the telephone, the microchip, the microprocessor had massive, massive life-changing impact for every single person in this room. But at the same time, there are positives too. Technology has allowed us to live in a world where, we do work less and we get luxurious goods and we get better food, etc., etc. Artificial intelligences will also change society for the better. So if you feel both anxious and excited, I think that's a pretty normal reaction to all of this stuff. I don't believe artificial intelligence is a solution looking for a problem. I think there's lots and lots of real-world applications already that it's been used for successfully. Number two, I do think it's going to radically change the work every single one of us does in this room. And what that means for us and what that means for our children is going to be exciting to sort of see and exciting to see unfold. But what comes next is not a technical choice. It's a series of political choices and questions that have to be answered. The answers to those questions or the choices we make will not just affect us and our kids, but the trajectory of the whole human race. And on that happy note, I will say thank you and have a great day.